3.1 is about introducing the derivative, and the idea of the derivative is finding the slope of a tangent line. So if you look at the graph here, at the point x equals a, that's the point here on the graph, the derivative of f of x, which is the function at x equals a, tells us the slope of the tangent line at x equals a. So the derivative tells us the slope of this red line here. Notice the tangent line touches the graph in a single point. It just touches the graph at x equals a. Nowhere else does it touch the graph. That's the defining characteristic of the tangent line. And the derivative of f of x at x equals a just gives us the slope of this red line. So to find that, we have to use things called the secant line. Now the reason why is because when I'm looking to find the slope of a line, the slope is rise over run. And the rise is your y values. And the run is given by your x values. But notice I need 2 points to find the slope. I need the first point, x1, y1, and the second point, x2, y2. The reason it's tough to find the slope of the tangent line is because there's only one point we have on the tangent line, and that's x equals a. So we only have x1. We don't have x2. So we look at secant lines. Now what a secant line is it's the slope between 2 points on a graph. So this black line here is the graph of f of x. And if you look at these blue dots, these are what we call the point x. And a is where we start from. And the secant line is the slope of the line between a and another point on the graph, in this case x. So you see this first blue line is the secant between a and this x out here. If x were to move closer to a, as here, well, as soon as x moves here, now we have a different secant line. This is between the point P and here, both of which are on the graph. And notice as this x point, the second point we look at, gets closer and closer to a, these blue lines have a slope that gets closer and closer to the slope of the red line. And that red line is the tangent line. So what this graph shows is the secant lines, which are lines between 2 points on a graph. As the second point, x, gets closer to the starting point, a, you see these secant lines getting closer and closer to the tangent line at x equals a. So the tangent line to f of x at point P is given in red. Its slope is m tangent here in the graph. The secant lines to f of x between x and a are in blue. And as x gets closer to a, those blue lines get closer and closer to the red tangent line. So as x gets close to a, the secant line between x and a approaches the tangent line of a. And so that's what this graph is telling us, and that's what this equation tells us as well. The slope of the tangent line is just the slope of the secant line. That's what f of x minus f of a over x minus a gives us. y2 is the y value at x. So there's our y2. y1 is the y value at a, and that's what f of a represents. It's our y1. X is our second x value. A is our first x value. So that's just the slope of the secant line between 2 points. Now as x gets close to a, that's what the limit tells us. As x approaches a, the slope of the secant line equals the slope of the tangent line. So another way to write this equation is the slope of the tangent line is the limit as x gets close to a of the slope of the secant line. And that's what the graph above shows. As the second point of the secant line gets closer and closer to a, the graphs of these secant lines get closer and closer to the graph of the tangent line. And so now we can actually find a derivative. Let's find the derivative to f of x equals x squared plus 1 at the point x equals 3. Well, this red dotted line is the tangent line I'm trying to find. And I find the derivative of the tangent line, that'll give me the slope of that red line. That's all the derivative does. The derivative of f of x at x equals 3 is the slope of the tangent line at x equals 3, which is the slope of this red dotted line. Now to find the slope, I need 2 points, y1 and x1, y1, and x2, y2. Well, I have the first point. That's the starting point that was given here. I know I have x equals 3 as one of my points. Well, how do I find the y value that goes with that? Well, that's what f of x does. Remember, f of x is just another way to write y. So if I want to find the y value here, the y value is just 3 squared plus 1, which is 10. So there's my first point. My x1, y1 turns out to be the point 310. This is the point that's on the graph. That's where I'm finding the tangent line. But I need an x2, y2 as well. And to do that, I can't use 3 anymore. I need a second point. And the problem is I don't know any second points on the red dotted line. So what I'd like to do, as we noticed above, if I stay really close to 3, then my secant line is going to be really close to my tangent line. So I'd like to get as close to 3 as I can, so I can get as close to the actual slope. I need a second point to make a secant line, but I'd like the secant line to be close to the tangent line. So I could say, what's the smallest amount I could move over? Well, you could move over 1. Well, I could move smaller than that. How about 0.1, or 0.01, or 0.01, or 0.001, or 0.0001? Smaller and smaller. We can't use a number, because you can't think of the smallest number to move over. So I'm going to use a letter, and I'm going to call the letter h. And h is how big of a step from 3 I take to the right. So the second x value is going to be 3 plus h, because I added h from 3 to the right. And the y value that goes with this on the graph, we found this one was 10. This y value, our second x value, is 3 plus h. And to find the y value that goes with that, I use the same equation. X squared plus 1 tells me the y value on the graph. So if x is 3 plus h, then the y value is going to be 3 plus h squared plus 1. Now to do that, I have to FOIL that. That's 3 plus h times 3 plus h plus 1. And when you FOIL that together, you get 9 plus 6h plus h squared plus 1, which is 10 plus 6h plus h squared. So what I just found out was my x2, y2. Notice what I did was I used the letter h to tell me how far over I go. When I do that, it'll make my secant line really, really, really close to my tangent line. The blue line I just drew would be the secant line between those 2 points. And so now I have my 2 points to plug into my slope formula. My x2, y2 turns out to be 3 plus h, because that's the new x value. And the new y value is 10 plus 6h plus h squared. Now the nice thing is, you tell me what h is. If h is 0.1, then I can put 0.1 in here for h and get the actual x value and y value. If h is 0.01, I can put in 0.01. If h is 0.001, I can put in 0.001. So this lets me make h as small as I'd like. Oops. Well, now I can take my 2 points, my x1, y1, and x2, y2, and plug them into my slope formula to figure out what the slope of the secant line is. It's a secant line because both of these points are on the graph. They're connected by this blue line. Both of these points lie on the graph. So it's a secant line that I'm finding. y2 minus y1 over x2 minus x1. That's just the slope. And the slope of the secant line, my y2 is 10 plus 6h plus h squared. Aha, that was just a subscript error there. I wrote h sub 2, but it should be h squared. I just copied it down wrong. Minus, my y1 is 10, my x2 is 3 plus h, minus my x1 is 3. So notice in my slope formula down here for the slope of the secant line, y2 is that, y1 is that. So I can label these so they're easier to see. This right here is my y2. This right here is my y1. That right there is my x2. And that right there is my x1. And so now I can actually calculate the slope. The slope of the secant line, 10 minus 10. These things here add to 0. And all I have left on top is 6h plus h squared over, if you notice on the bottom, 3 and negative 3, add to 0. Now that's left is h. So you tell me what h is, I'll plug it in here for h, and I'll have the slope of the secant line, the blue line. But the smaller h is, the closer it is to the red line. To actually make the blue line lie on the red line, that h would have to be 0. I would have to not move at all to get the slope of the red line. The h would have had to have been 0, no movement. But I can't put 0 in for h because there's an h on the bottom, and I can't put 0 on the bottom. Remember, the slope of the tangent line is the limit. But I would like h to be as small as possible. What's the smallest h can be? The smallest h can be is 0. But I can't plug in 0 for h because h is in the denominator. But I can take the limit as h goes to 0, which means I can get as close to 0 as I want. And the closer I get to 0 for h, the closer I line up to the red tangent line. Well, I can factor this. Remember, when you're calculating a limit, you can plug in. In this case, I can't plug in because I get a 0 on the bottom. If that happens, you should try to factor this, because after you factor it, you may be able to plug in. I can factor an h out of the top. It'll cancel the h on the bottom. And this turns out to be the limit as h goes to 0 of 6 plus h. Well, now that I've simplified this, I can actually plug in 0 for h, because I've canceled it out of the bottom. When I plug in 0 for h, I get 6. Well, what does 6 tell me? That 6 is the derivative of x squared plus 1 at x equals 3, which is the slope of the tangent line, 2x squared plus 1 at x equals 3. So this is the derivative 2f of x equals x squared plus 1 at x equals 3. And that's what we were asked to find. But what that also means is this is the slope of the tangent line. 2f of x equals x squared plus 1 at x equals 3. Because remember, the derivative is the same thing as the slope of the tangent line. So all we really did was figure out the slope of that red line, which we found out to be 6. But this can be a little tedious, because what if I wanted to find the derivative at x equals 2, or x equals 5, or x equals negative 8? Notice these tangent lines are different at different points. If I were to look at negative 2 and see what that tangent line looked like, the tangent line at negative 2 would have a negative slope. Forgive my bad tangent line. But that green line is an impression of what the tangent line at negative 2 would be. Notice it has a different slope than the red tangent line at 3. So to find the derivative this way for each single point would take forever if I wanted to find it at more than one point. So at x equals 3, it's 6, but this doesn't tell me what it is at x equals negative 2. So ideally what I'd like to do is come up with an equation for the derivative, which would be an equation for the slope of the tangent line. And then you tell me where on the x-axis you are. I'll plug it into the derivative, and it'll tell me the slope there. So I'd like to come up with a general derivative, not one at a specific point. I'd like to come up with a derivative for any point, where I just have to plug in where I'm at to figure out the derivative. I don't have to do this every time. Well, first we should talk about some notation for derivatives. The derivative of y equals f of x can be written many ways, but here are the 4 most common. Remember, y and f of x are the same thing, 2 ways to write the same thing. But the derivative could be written as f prime of x, that's how that's read, or y prime of x, because f of x and y are the same thing. Or this d over dx notation, which is actually a clearer way to write the derivative, and you'll see this later with implicit derivatives, or implicit differentiation. That's the act of taking a derivative is called differentiation. But I have f prime of x, which is a way to write the derivative, or I could write y prime of x. Sometimes you'll just see y prime instead of y prime of x. df of x over dx. Sometimes you'll see df over dx. dy over dx. Same idea. So these are four notations. Sometimes they don't put the x in. That's what that stuff tells you. Sometimes they'll write f prime as well. So when instead of writing out the derivative of f of x, that whole sentence can be written as f prime of x. These are equivalent ideas. And look at how much time I saved. Haha. But f prime of x, y prime, df, dy, all those are the same way. Instead of writing out the sentence, the derivative of f of x, you can just write that symbol. It means the same thing. So let's find a general derivative. Instead of having to do this for each point on the graph, we can come up with a general derivative to x squared plus 1. And the general derivative will give us an equation in terms of x for the slope of the tangent line for the derivative. And all I'll have to do is plug in where I'm at to figure out what the slope is there. And to do that, I can't have 3 here anymore because it's a specific point. So I'm just going to use x. And so the y value at x is f of x. So at x, the y value is x squared plus 1. And I'm going to do the same little trick by moving over to the right h. So the second point is going to be x plus h more to the right. And at x plus h, to find the y value, you just replace every x with an x plus h. Now I have to FOIL that. Which turns out to be x squared plus 2xh plus h squared plus 1. So I have my 2 points for my slope. Here's my first point, and here's my second point. It's the same trick we played before to find f of x plus h and f of x. And this is a secant line, because both of these points are on the graph. And I'm going to use the slope formula to find the slope of that blue secant line. And the slope formula is y2 minus y1 over x2 minus x1. Well, my y2 is this f of x plus h, minus my y1 is f of x. My x2 is x plus h. My x1 is x. If you look at the bottom here, the x's add to 0, plus x and minus x. So this becomes f of x plus h minus f of x over h. And this is a very special thing. If you've taken pre-calculus, maybe even some algebra classes, you hear about this. This is called the difference quotient. Difference because you're subtracting on top. Quotient because you're dividing. The difference quotient is just the general form for the slope of the secant line, where you just move over h, this little itty-bitty step h. And this works for any function in the world. F of x plus h, you plug in x plus h as your second point. F of x, you plug in x as your first point. And the x plus h minus x just leaves an h in the bottom. Well, if I want to find the slope of the tangent line, the slope of the tangent line just turns out to be the limit of this as h goes to 0. This is the nicest way to find the derivative, because remember, the slope of the tangent line is just the derivative. And so we're going to use this to find a general formula for the derivative. So I'm going to use my points to find a formula for mine. But here's my general difference quotient, f of x plus h minus f of x over h. So I'm going to plug in my x plus h and x. This is f of x. This is f of x plus h. So I'm going to plug them in here, and we're going to see how this formula works out. So my f of x plus h is the second y value here. It's x squared plus 2xh plus h squared plus 1. That's my f of x plus h. That's what I got when I plugged in x plus h. Now I have to subtract f of x. That's what I get when I plug in x. It's the y value I get when I plug in x. But when I subtract f of x, I have to subtract the whole thing. So I always have to put f of x in parentheses. Later on, if you make a mistake, you'll know you made a mistake because all the stuff without h's won't cancel on top. And if that happens, it means you probably didn't put f of x in parentheses. So if I want to find the slope of the tangent line, I want to take the limit of this as h goes to 0. Now I have x squared plus 2xh plus x squared plus 2xh plus h squared plus 1. I'm going to distribute that negative sign and get negative x squared minus 1. And there's an h on the bottom. Notice I can't plug in 0 for h because h is on the bottom. But I should be able to simplify to cancel that h on the bottom. A positive x squared and a negative x squared add to 0. A positive 1 and a negative 1 add to 0. So what I'm left with is something I can simplify. This is the limit as h goes to 0 of 2xh plus h squared over h. All the stuff without h is canceled on top, which is what's supposed to happen if everything works out right. Because I can factor that h out of what's left and cancel the h on the bottom, which will let me plug in to figure out what this is. So the slope of the tangent line turns out to be the limit if h goes to 0 of 2x plus h, which is 2x plus 0, because now I can put in 0 for h, because there's no 0 in the bottom of a fraction. I simplified. And it works out to be 2x. The slope of the tangent line is 2x. But what is another name for the slope of the tangent line? The derivative is the slope of the tangent line, f prime of x. So this tells me a general equation for the derivative. It says the derivative of x squared plus 1, the derivative we just found out from a moment ago, the derivative is 2x. So this allows us to find the slope of the tangent line anywhere. Let's look at what happened where we had before. Before, at the very beginning, we wanted to find the slope of the tangent line at x equals 3. Well, to do that, I can just plug in 3 for x into the derivative. And I get 6, which is the same answer I got before. But the nice part is now I can do other values of x. It doesn't just have to be that value. I can do values like x equals 2 or x equals negative 1. So to quickly see what's happening here, I have to make myself a little bit of room. And I can find the derivative at x equals negative 2 now. By just plugging in negative 2 into my equation. So now I know the slope of the tangent line at negative 2 as well. At 3, the slope of the tangent line is 6. At negative 2, the slope of the tangent line is negative 4. So it's easier to come up with an equation for the derivative, and then you can find the slope of the tangent line anywhere on your graph. So here are the equations that we've worked through in general. If you want to find the derivative at a specific point, x equals a, in our previous example it was x equals 3. What's the limit as h goes to 0 of a plus h minus f of a over h? The second example where we came up with the derivative as a function, well, that's the limit as h goes to 0 of x plus h minus f of x over h. Notice if you're at x equals a, you just replace your x's with a's. That's the only difference. If you're at a given point, x equals a, then all you do is replace your x's with a's. But a lot of times it's easier to come up with a general equation for the derivative, and then we can find the derivative at any point. So let's try it here. Finding the derivative of x squared plus 2x plus 1 at x equals 3. We're given a specific point here to find the derivative, so we can use the first version, the limit as h goes to 0 of f of a plus h minus f of a over h. That's just the difference quotients where the x's are replaced with a's. So I gotta figure that stuff out. F of a, in this case a is 3. So if I want to figure out f of a is 3, so it's the limit as h goes to 0 of f of 3 plus h minus f of 3 over h. So we're going to figure out f of 3 plus h and f of 3. And that's what I'll do in this little space here. F of 3. What that means is to replace every x with the number 3. And I get 9 plus 6 plus 1, which is 16. That's f of 3. Well, I also have to figure out f of 3 plus h. Well, that's 3 plus h squared plus 2 times 3 plus h plus 1. Notice all my x's got replaced with 3 plus h's. So let's simplify this. 3 plus h, 3 plus h, 2 times 3 plus h plus 1. So I FOIL. When I FOIL that, I get 9 plus 6h plus h squared. I'm going to distribute the 2 into the 3 and the h, and I get 6 plus 2h plus 1. And I can put the numbers together, a 9 and a 6 and a 1, giving 17. 6h plus 2h gives me 8h plus h squared. So with a little bit of algebra, I figured out what f of 3 plus h is. It's 9 plus 6 plus 1 gives me 17. 6h plus 2h gives me 8h, and there's an h squared. So to find the derivative, and this is what another way to write the derivative at 3, f prime of 3, that's the limit as h goes to 0. F of 3 plus h is 17 plus 8h plus h squared minus f of 3 is 16 9 plus 6 plus 1 is 16. 9 plus 6 plus 1 is 16. Having trouble here adding for some reason. Yes, 9 and 6 and 1 is 16. So 16 plus 8h plus h squared minus 16 over h. Notice 16 minus 16 adds to 0. And so this is the limit as h goes to 0 of 8h plus h squared over h. Notice I still can't plug in 0 for h yet because h is in the denominator. But I can simplify this. I can factor in h out of the top. I'm left with 8 plus h. but now the h's will cancel. And so this is the limit as h goes to 0 of 8 plus h. And now I can plug in. And I find out the derivative of this function at x equals 3 is 8. So the derivative at 3 is 8. That means the slope of the tangent line at x equals 3 is 8. Well, let's find some more derivatives. Let's try it again. 1 over x squared at x equals 2. Well, to find the derivative at x equals 2, that's really just the slope of the tangent line at x equals 2. And it's the limit as h goes to 0. F of 2 plus h minus f of 2 over h. And I need to figure out what f of 2 plus h and f of 2 are going to be. So I can do that over here on the side. So I'll do on the side and I'll work these out. So, first we'll calculate f of 2. F of 2 is what I get when I plug in 2 for x, which is 1/4. Now I'm also going to need to plug in 2 plus h in place of x, and this becomes 1 over 2 plus h squared. And so now, if I want to figure out what this derivative is, I can plug into this formula. The limit as h goes to 0. F of 2 plus h is 1 over 2 plus h squared. F of 2 is 1 over 4. It's all divided by h. Now we can't cancel that h in the bottom at all at the moment. So we're going to have to simplify this. The way we simplify it is by combining the fractions. To combine the fractions, we need a common denominator. The common denominator is 4 times 2 plus h squared. So I'm going to rewrite these so they have a common denominator, so I can subtract them on the top. Well, to get to the common denominator here, I have to multiply by 4 over 4. You got to multiply by the number 1, otherwise you change what you start with. So now the denominator will be 4 times 2 plus h squared. I just multiply by the number 1. I'm going to do the same thing over here. I need a 2 plus h squared on the bottom. But if I put one on the bottom, I should put one on the top as well to make the number 1. So the derivative at x equals 2 is the limit as h goes to 0. Now I can find a common denominator. The first one is 4 over 4 times 2 plus h squared minus 2 plus h squared over 4 times 2 plus h squared all over h. Just found the common denominator. And now that I have a common denominator, I can go and put these fractions together. What's the limit as h goes to 0 of 4 minus 2 plus h squared over 4 times 2 plus h squared all over h. Now I'm going to FOIL that out on top. It's 4 minus 2 plus h times 2 plus h. That's 4 plus 4h plus h squared over 4 times 2 plus h squared over h. All I did was FOIL 2 plus h times 2 plus h, and that gives me 4 plus 4h plus h squared. More algebra. Yay! I still can't cancel that h, so I have to simplify some more. This is the limit as h goes to 0. I'm going to distribute that negative sign inside there. 4 minus 4 minus 4h minus h squared over 4 times 2 plus h squared all over h. And you notice that plus 4 and minus 4 will add to 0. So I'm getting a little closer. This is the limit as h goes to 0 of minus 4h minus h squared over 4 times 2 plus h squared over h. Doesn't quite look like I can cancel that h yet, but I can write this h on the bottom as a fraction. And dividing two fractions is like multiplying by the reciprocal of the denominator. So this is negative 4 minus h squared over 4 times 2 plus h squared times the reciprocal of h over 1, which is 1 over h. You'll notice that this should be at minus 4h here. I had a mistype. It should be minus 4h. Well, now I can factor an h out at the top. And so negative 4h minus h squared, when I factor out an h, gives me negative 4 minus h. But you'll notice these h's cancel. I canceled the h that used to be in the bottom. So now, oh, I forgot my limit. Gotta remind myself what I'm doing. And so now it's the limit as h goes to 0. Minus 4 minus h over 4 times 2 plus h squared. But now I can plug in 0 for h, because when I plug in 0 for h, it doesn't make the bottom 0. So it's legal to plug in 0 for h. And so this is negative 4. So I just write it down again, and wherever I see an h, I'm going to plug in 0 now. And this turns out to be negative 4 over 4 times 2 squared. So we can actually calculate the derivative. The derivative at 2 is negative 4 over 16, which is negative 1/4. So the slope of the tangent line to 1 over x squared at x equals 2 is negative 1/4. And to calculate this derivative, we use the same formula. The limit as h goes to 0 of a plus h minus f of a plus h minus f of a over h. And notice it's all algebra. Calculus is glorified algebra. So we do all these algebraic steps. We can't cancel the h here. So we put the fractions together with common denominators. When we put the fractions together, some of the things cancel. And all the stuff on top just has h's in it. So I know I can factor an h out. So I multiply by the reciprocal of the denominator, factor an h out of the top, and cancel that one on the bottom. That allows me to plug in 0 for h to get this actual limit. What did the limit tell me? Well, it told me the derivative of f of x at x equals 2, which is the slope of the tangent line of f of x at x equals 2. We've been doing derivatives at single points, and that's good to know how to do. But it's better to be able to find a general formula for the derivative, because then you can plug in any point you want after you have the formula. So let's do some derivatives with general formulas now. Here's the derivative of x squared minus 9. Notice they don't give me an x value to plug in. Well, this is a general derivative, and it's going to be a function of x. So to find this derivative, it'll be f of x, because I don't have a number to plug in. And so it's x plus h, f of x plus h, minus f of x over h. The limit as h goes to 0 of the difference quotient. Well, I can find out f of x and f of x plus h I'll do that over here on the side. F of x is just x squared minus 9. I get that one for free every time. So that one I got. F of x plus h is what I have to find. F of x plus h just means replace x with x plus h. Well, in this case, I have to FOIL that x plus h squared. And when I FOIL that x plus h squared, I get x squared plus 2xh plus h squared. And then the minus 9 is there as well. So there's my f of x plus h, and there's my f of x. So to find the derivative, I can just plug those into the formula. It's the limit as h goes to 0 of f of x plus h. That's x squared plus 2xh plus h squared minus 9. And then I have to subtract f of x. But I have to subtract all of f of x. So I have to put f of x in parentheses. And this is all over h. Now again, I'd like to plug in 0 for h, but I can't because it's in the denominator. When I simplify the stuff on top, everything without an h should cancel. So I can factor an h out of the top to cancel the one in the bottom here. If that doesn't happen, odds are you forgot to put f of x in parentheses. That's usually what causes that problem. So I had to put my f of x in parentheses right here to subtract the whole thing. And so I'm going to distribute that negative. I'm going to subtract all of f of x squared plus 2xh plus h squared minus 9 minus x squared plus 9 over h. And I get that from distributing this negative sign inside there to both terms. And if you look at the top, you'll notice positive x squared and a negative x squared add to 0. Negative 9 and positive 9 add to 0. And so my derivative, the limit as h goes to 0 of 2xh plus h squared over h. Now I can cancel that h on the bottom because I can factor an h out of the top. The limit as h goes to 0 of h times 2x plus h over h. The h's will cancel. That's the limit as h goes to 0 of 2x plus h. I can find that limit now because I can plug in 0 for h because I canceled it out of the denominator. And so my derivative here becomes 2x plus 0, which is just 2x. That's the slope of the tangent line. It's an equation to find the slope of the tangent line to x squared minus 9. You tell me where you are on the x-axis, I'll plug it in here and tell you the slope of the tangent line to x squared minus 9 then. So it's the same process, but it finds a general derivative. Again, that's all algebra. The only calculus step is this last step here, where I plug in 0 for h. That's the calculus step. The rest of it's algebra. So we can do another derivative. See what else we have. Yes, a couple more derivatives in here. One of them is for 1 over x. Let's find the general derivative of 1 over x. And so to do that, I use the formula, the difference quotient formula, the definition. The limit as h goes to 0 of f of x plus h minus f of x over h. Just like before, the trick is to find f of x plus h and f of x and plug them in. Well, I already have f of x. F of x they gave me for free at the very beginning. It's 1 over x. If I want to figure out what f of x plus h is, I just replace every x with an x plus h. So now I have f of x and f of x plus h. I can put them inside the formula here. The limit as h goes to 0. F of x is 1 over x plus h. That's f of x plus h, I'm sorry. F of x plus h is 1 over x plus h. F of x is 1 over x. And the whole thing is over h. Now we had a similar problem to this before. We can't cancel the h's, so all that's left to do to simplify this, the h on the bottom we can't cancel. So all we have left to do to simplify this is to put the fractions together. And to do that, you need a common denominator. The common denominator in this case is x times x plus h. So I'm going to have to rewrite this so I can have a common denominator for these fractions. Well, I need an x in the bottom of the first one for a common denominator, and I have to put the one on top to make the number 1 that I'm multiplying by. I need an x plus h in the bottom of the second denominator, and so I'll need an x plus h on top so that I make the number 1 that I'm multiplying by. So this is just to find the common denominator between two fractions. And it's the limit as h goes to 0. Now I have x over x times x plus h minus x plus h over x times x plus h. And the whole thing has a big H on the bottom. That H on the bottom doesn't let me plug in my H from the limit because it would make it undefined. But now that I have a common denominator, I can subtract those two fractions. The limit as h goes to 0. I have x minus h. I'm subtracting all of this second fraction. So I'm subtracting the x and I'm subtracting the h over the common denominator, x times x plus h. And the whole thing is divided by h. And if you notice on top, the x and the minus x add to 0. And so all that's left on top is stuff with h's in it. A negative h, to be specific. Negative h over x plus h divided by h. Well, now that all that stuff without h's cancels, I have an idea that I can get this h to go away in the bottom and then actually plug in 0 for h. But to do that, I have to think about h on the bottom as h over 1. When you divide two fractions, it's like multiplying by the reciprocal of the denominator. The reciprocal of h over 1 is 1 over h. And notice these h's cancel. And so now my derivative, f prime of x, is the limit as h goes to 0 of negative 1 over x times x plus h. But now I can plug in 0 for h, because it won't make the denominator 0. And so, f prime of x is the limit as h goes to 0. I should probably just write this all in one big swoop. I can plug in 0 for h now into my original one. Because it won't make a 0 show up on the bottom. And my derivative turns out to be negative 1 over x squared. So the slope of the tangent line to 1 over x is negative 1 over x squared. You tell me where you are on the x-axis, and I'll plug it into negative 1 over x squared to figure out the slope of the tangent line to 1 over x there. And again, it's a lot of algebra. We're trying to simplify these fractions by combining them. Oh, there's another derivative we can play with, and we'll draw some graphs. So here's the last derivative we're trying to find. It's f of x is the square root of x. And just like before, if you want to find the derivative, you have to look at the limit as h goes to 0 of f of x plus h minus f of x over h. And it's the same thing we had before. We need to figure out f of x plus h and f of x. Well, f of x they gave me. F of x is the square root of x. F of x plus h just means we place every x in there with an x plus h. So, I can start working with this formula. This is the limit as h goes to 0. F of x plus h is the square root of x plus h. F of x is the square root of x. And the whole thing is divided by h. Well, there's no way I can cancel that h out of the bottom now. And these aren't fractions, so I can't add them together. But if you think back to complex numbers, there's a thing called the complex conjugate, which is what you get when you change the sign in front of the I. So 2 plus 3i and 2 minus 3i are complex conjugates. There's the same thing with square roots. They're called the radical conjugates. And whenever you have square roots that you're trying to simplify with a limit, you should use the radical conjugate to help you do that. So in this case, I can find the radical conjugate. Radical is just another name for a root sign. The radical conjugate I want to use turns out to be the square root of x plus h plus the square root of x. Notice all I do is change the sign between the roots. So I want to multiply this radical conjugate times the stuff on top, because it'll help the square roots go away. But if I multiply this stuff, so whenever you see square roots in a derivative and you're trying to simplify to cancel the h, you always use the radical conjugate. And the way you find the radical conjugate is to change the sign between the square root signs. And when you do that, it'll help make the square roots go away on top, so h's will pop out, then you can cancel the one on the bottom. But if I multiply the top by the radical conjugate, I also have to multiply the bottom by it to make the number 1, so I don't change anything. So to finish this derivative, the limit as h goes to 0. Here's the derivative I have, or what I have written, square root of x plus h minus square root of x over h. I'm going to multiply the top by this radical conjugate, square root of x plus h plus the square root of x. But since I did it on top, I also have to do it on the bottom to make the number 1, so I don't change the fraction I started with. So I multiply the top and the bottom by the radical conjugate. And notice I'm going to have to FOIL on top, which will be loads of fun. But I'm going to leave the bottom just like it sits, h times square root of x plus h plus square root of x. Because I'm just trying to cancel that h out of the bottom, and if I go and distribute it in there, it'll be harder to see where to cancel it. So I'm going to leave the h out on the bottom. So it'll be easier for me to cancel it though. I'm going to have to work out the top so I can try to get an h to pop out to cancel the one on the bottom. So the first two is square root of x plus h and the square root of x plus h. The middle one, or outer one, is square root of x plus h times square root of x. The inner one is negative, is square root of x plus h times negative square root of x. And the last one is negative square root of x times square root of x. So all I did was do first, outer, inner, last. I FOILed those together. Now this is the square root of x plus h squared, because it's multiplied by itself. So this right here is the square root of x plus h squared. And this right here is the square root of x squared. Notice the square and the square root erase each other. Oh gosh, I forgot my limit. So square root of x plus h and the square root of x plus h is the square root of x plus h squared. And the square and the square root go away. All I'm left with is x plus h. This is a positive root x plus h root x. This is a negative root x plus h root x. When you add these two things together, you get 0, because they're the same thing. One is positive and one is negative. The last two, square root of x times square root of x, is square root of x squared. And the square and the square root go away. So I just get minus x. On the bottom, I have h, square root of x plus h, plus square root of x. That's what the conjugate does. The conjugate makes the square roots go away. So I wanted to multiply the top by the radical conjugate so I could get the square roots to go away. And notice when the square roots go away, plus x and minus x add to 0. And all I have left on top is an h, which will let me cancel that h on the bottom. So that's what the radical conjugate does for you. It makes the square roots go away on top. And when the square roots go away on top, it'll let you cancel that h on the bottom. And so the derivative turns out to be the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. But if I put 0 in for h, it won't make the denominator 0 now, because I canceled the one that causes the problem. So I can do that now. And I get 1 over the square root of x plus 0 plus the square root of x. So I just put in 0 for h now, because it was legal. And it's 1 over the square root of x plus the square root of x. Well, that's 2 square root of x's, so it's 1 over 2 square root of x. So we just found out that the derivative of the square root of x is 1 over 2 square root of x, or the slope of the tangent line to the square root of x is 1 over 2 square root of x. You tell me where you are on the x-axis, and you walk on the graph square root of x, and I'll plug it into 1 over 2 square root of x to figure out the slope of the tangent line there. So again, another type of derivative that you can find when you see square roots. You should use the radical conjugate to help you make the roots go away. There's one more topic we have to look at, and that's being able to draw the graph of a derivative if I give you the graph of a function. So here are a couple graphs of functions, and below them, I'm going to draw their derivative. Now to draw the derivative, this can be really confusing, so it's good to take a good look at these when you do it. But I'm going to draw the derivative right below them. Now remember, all the derivative is the slope of the tangent line. So before I draw my derivative, I'm going to put some tangent lines on this graph. I'm going to draw them a little, just kind of see what's happening with them. Probably too many tangent lines, but let's see if we can draw it. So over here, right here on my graph, the y value here is going to be the slope of that line, which is a bigger positive number. Notice as we move from the left to the right, the slope of this red line gets smaller and smaller and goes to 0. Right here at the top of this curve, I have a horizontal tangent line, which has a slope 0. So right here at the top of the curve, the slope is going to be 0, because that's the slope of that red line there. It's horizontal. If you look on this side of it, if you look to the right, or to the left of it, over here on the left, you'll notice that I have a really big positive slope that gets smaller and smaller and smaller and ends up at 0 here. Well, remember that the derivative, the graph of the derivative is just the slope of the tangent line. So on the graph of the derivative, the y value should be the slope of these red lines, because these red lines are the tangent lines. The derivative is the slope of the tangent lines. So the y value of the derivative should be the slope of these red lines. So to the left, I have a big positive slope that slowly goes to 0. So I have to draw this line so that I have a positive slope that goes to 0. Big positive slope, smaller positive slope, smaller positive slope, 0 slope. Notice the y values here are just giving me the slope of the red lines on the graph. The tangent line here is a big positive number. If I scoot over a little bit, the tangent line there is a smaller positive number. The slope of that tangent line there is an even smaller positive number. The slope of the tangent line here is 0. Now if I look here, the slope of the tangent line there is negative. It's a small negative number. And as I move to the left, the slope of the tangent line gets more negative. It gets to be a bigger negative slope. So as I move to the left, the slope of this line gets to be a bigger and bigger negative slope. So this is a graph of the derivative of that function. And we can look and examine how this is happening here. Right here, the slope of the tangent line is a big positive number. So the y value of the derivative is a big positive number there. As I move to the left, the slope is still positive, but it's getting a little smaller. So the y value is still positive, but it's getting a little smaller. As I move further to the left on f of x, that slope is still positive, but it's almost 0. As I move further to the left on the derivative there, the slope is still positive, but it's almost 0. The y value is still positive, but it's almost 0. Notice the slope matches the y value. Big positive slope, big positive y value. Smaller positive slope, smaller positive y value. Here's a horizontal tangent line. The slope of a horizontal line is 0. So the y value of the derivative is 0 there. If I look here, I have a small negative slope. So the y value is a small negative number on the derivative. And here I have a steeper negative slope. So the y value is a lower negative number. It's a steeper negative number. We're going to try that same process on the graph to the left here. Here's a graph of f of x. I would like to draw a graph of the derivative, f prime of x. The easiest way to do that is to figure out where the slope is going to be 0. The slope of the tangent line. So that happens where these bumps are. If I look right here at these hills, there's going to be a tangent line that's horizontal, has a slope 0. So right here, the slope of that tangent line, the slope of the red line is 0. So the y value of the derivative there has to be 0. Right here, at the bottom of that valley, the slope of the tangent line is 0. So the y value of the derivative there should be 0. Here at this red line, the slope of the tangent line is 0. The slope of that red line is 0. So the y value on the derivative there should be 0. And then we can look at what's happening to the tangent lines around it. So here's the first 0, and we're going to look to the left of it. So this is the first place where the slope is 0, right here, to the left of that. That's a positive slope to that red line, and it's a big positive slope. And as I move to the right, notice the slope is still positive, but now it's smaller and smaller until it hits 0. So the y value over here has to be a big positive number that gets smaller and smaller until it hits 0. So we can look at why this works. Big positive slope, big positive y value. Smaller positive slope, smaller positive y value. The slope of the tangent line is 0, the y value is 0. Now we can go in between here. That's a negative slope that starts off by getting bigger, and then it shrinks back down to 0. So that means I need a slope to become negative, and then turn around and go back to being 0 again. So what'll happen is, the y value will be negative, and turn around and come back to being 0 again. So we can look at why that works. The slope is 0, the y value is 0. Now the slope is a negative number, the y value is a negative number. The slope is still negative, but it's getting closer to 0 again. It's still negative, but it's getting closer to 0 again. Here the slope of that tangent line is 0. Here the y value is 0. And we can do the same thing here now. Positive slope gets less positive, goes back to 0. Positive y value gets less positive, goes back to 0. Small positive slope gets a little bigger, goes back to 0. Small positive number gets a little bigger, goes back to 0. Here the slope of the red tangent line is 0, so the y value is 0. Now the slope is a little bit negative and a bigger negative. So the y value is a little bit negative and bigger negative. So the red graph here would give me a graph of the derivative of f of x. I'm looking at the slope of these red tangent lines and using that to find the y value of the derivative. So we've talked about some examples now of finding derivatives, finding slopes of tangent lines, and being able to use the derivatives to look at graphs and come up with graphs of derivatives of functions. So this is the ideas behind 3.1. In the next chapter, 3.2, or next sections, 3.2, 3.3, 3.4, have to do with shortcuts to this long limit process. So that'll be in the next section.